The morning of March 4th, 1943 broke cold and clear over Hamm, Germany. Oberst Friedrich Weber stood on the roof of the Westphalian Railway Works Administration Building, binoculars raised toward the western sky. As the Chief Air Defense Coordinator for the Ruhr Industrial Region, Weber had spent the last 3 years watching British bombers turn German cities into funeral pyres. But the British came at night, hidden by darkness, dropping their bombs blindly across entire neighborhoods. What Weber saw approaching at 10:30 that morning was something entirely different. Contrails. Dozens of them, perfectly straight white lines scratched across the blue sky at an altitude Weber's flak crews called the Death Zone. 25,000 feet, maybe higher. At that altitude, the air was so thin and cold that human blood would boil without pressurization. The temperature outside those aircraft was -60 degrees Fahrenheit, and yet the Americans were up there, flying in broad daylight, in perfect formation, heading directly toward his railway complex. Weber had read the intelligence reports from occupied France. American B-17, flying fortresses, conducting what they called precision daylight bombing. The Luftwaffe pilots who'd engaged them reported formations so tight that defensive fire created an impenetrable wall of Turksint, 50 caliber bullets. But precision? From 5 miles up? Weber didn't believe it. No one could aim a bomb from that altitude with any accuracy. The British had tried daylight bombing in 1939 and 1940. The results had been catastrophic, not for German industry, but for British bomber crews. They'd lost so many aircraft that Bomber Command abandoned the concept entirely and switched to nighttime area bombing. The Hamm railway complex sprawled across 400 acres. It was the second largest marshalling yard in Germany, handling 12,000 rail cars daily. Destroying it would require hitting specific repair shops, the main roundhouse, the classification yards, and the signal tower, all spread across nearly half a mile. Hitting any of those from 25,000 feet seemed mathematically impossible. Weber watched the lead formation align itself on an approach vector. The bombers weren't weaving or taking evasive action. They flew straight and level, as if the 88mm flak batteries below didn't exist. The guns opened up, black puffs of smoke erupting around the formation at staggered altitudes. Weber saw one bomber's wing flash as shrapnel tore through it. The aircraft held position. Another took a direct hit to its tail section. It dropped out of formation, trailing smoke, but the others maintained their precise spacing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Then the bombs began falling. Weber could see them, tiny black dots, tumbling from the lead bomber's bay, followed instantly by every other aircraft in the formation releasing simultaneously. 18 bombers, 108 bombs, approximately 54,000 pounds of high explosive, all released within a 2-second window. The bombs didn't scatter randomly across the landscape. They fell in a concentrated pattern, a lethal rectangle, maybe 400 feet long and 200 feet wide. Weber watched through his binoculars as the first impacts walked directly through the main roundhouse. The building vanished in a rolling series of explosions. The classification yard where locomotives received maintenance, gone. The signal tower that controlled all traffic through the complex, obliterated. The repair shops where damaged rolling stock was refurbished, collapsed into burning wreckage. The entire strike lasted less than 90 seconds, from first bomb release to final impact. When the smoke cleared enough for assessment, Weber stood staring, at destruction so precise it seemed surgical. The administrative building where he stood, 300 yards from the main complex, remained untouched. The worker housing blocks another 200 yards beyond, intact. But the actual railway infrastructure, the components that made Hamm functional as a transportation hub, had been effectively erased. Weber lowered his binoculars and spoke to his assistant without looking away from the devastation. "Get me Berlin. Tell them the Americans can actually aim." That single mission over Ham represented the culmination of nearly 15 years of engineering obsession, $2 billion in development costs, and a technological revolution that most German military planners didn't believe was possible. The weapon that made it possible weighed 50 pounds, cost $8,000, contained over 2,000 precision parts, and was guarded more carefully than gold reserves. American bombardiers swore formal oaths never to discuss its mechanisms. Crews were ordered to destroy it with thermite charges before allowing capture. Intelligence services on both sides considered it the most significant technological advantage in the strategic bombing campaign. The Germans called it the Wunderwaffe der Amerikaner, the American wonder weapon. The British knew it only through classified briefings and grudgingly admitted its superiority over their own Mark 14 bombsight. The Americans simply called it the Norden, after the obsessive Swiss-born engineer who'd spent more than a decade perfecting a machine that could, theoretically, drop a bomb into a pickle barrel from 4 miles up. Carl Norden never promised miracles lightly. When he told the United States Navy in 1921 that he could build a bombsight accurate enough to hit a 3-foot target from 20,000 feet, most engineers at the Naval Research Laboratory thought he'd lost touch with reality. The best bombsights in 1921, devices like the Mark I and the early Sperry prototypes, couldn't reliably hit targets within a quarter mile. Norden was claiming he could improve accuracy by a factor of 400. That wasn't incremental engineering improvement. That was claiming to rewrite the laws of physics. But Norden understood something about the bombing problem that everyone else had missed. The fundamental obstacle wasn't the bomb. Bombs followed predictable ballistic trajectories governed by gravity, air resistance, and forward velocity. Given accurate inputs about altitude, airspeed, and wind conditions, calculating the bomb's path was just mathematics. The real problem was the bombardier's reference frame. Every bombsight developed up to 1921 required the bombardier to manually track the target while the aircraft was moving, calculate dozens of variables, either mentally or with crude mechanical aids, and then estimate the correct release point. The bombardier was trying to solve a complex differential equation in his head while sitting in an unstable aircraft being thrown around by turbulence, with wind pushing the aircraft off course, with the target sliding across his field of view, and with perhaps 30 seconds to complete all calculations before overshooting the target entirely. Human beings simply weren't designed for that task. Reaction time delays, calculation errors, estimation mistakes, these human limitations imposed a fundamental accuracy ceiling that no amount of training could overcome. The best bombardiers in the world, men who'd flown hundreds of missions and developed almost instinctive bombing skills, still couldn't consistently place bombs closer than 200 or 300 feet from their aiming point under ideal conditions. Norden's revolutionary insight was that you could remove most of the human error by giving the bombsight its own stable reference frame, independent of the aircraft's movement. Instead of forcing the bombardier to compensate for every pitch, roll, and yaw of the aircraft, while simultaneously tracking the target and calculating trajectory, what if the bombsight itself could maintain a perfectly stable view of the ground, regardless of what the aircraft was doing? What if the machine could handle all the calculations automatically, continuously updating the solution right up until bomb release? The bombardier would simply keep the crosshairs on target. The machine would do everything else. This concept required technology that barely existed in 1921, gyroscopes. Not the toy gyroscopes that spin on a desk. Industrial-grade precision gyroscopes capable of maintaining spatial reference while subjected to extreme temperatures, violent vibrations, and rapid altitude changes. Gyroscopes that could spin at 8,000 revolutions per minute for hours without failure. Gyroscopes machined to tolerances measured in 10,000ths of an inch. In 1923, Norden founded Carl Norden, incorporated in a modest workshop in Brooklyn, New York. He took a Navy contract worth $75,000, approximately $1.3 million in today's currency, and essentially vanished into his workshop with one assistant engineer, Theodore Barth. For the next 4 years, the Navy heard almost nothing from him. No progress reports, no prototype demonstrations, no requests for additional funding or clarification of requirements. Navy administrators grew increasingly nervous. $75,000 represented serious money, and Norden wasn't providing any evidence he was actually accomplishing anything. Some voices within the Bureau of Ordnance argued for terminating the contract and demanding refunds. But Norden had built enough credibility through his earlier work on naval gun stabilization systems that the Navy reluctantly allowed him to continue. In 1927, Norden finally emerged from his workshop with a working prototype designated the Mark 11. The device looked like something from a mad scientist's laboratory, a complex assembly of gears, mirrors, and gyroscopes mounted on a precision gimbal system, all enclosed in a metal housing that weighed approximately 40 pounds. Norden personally transported it to the Navy's Aberdeen Proving Ground in Maryland and conducted live drop tests. The results were classified immediately, but word spread through military channels with the speed of wildfire. Norden had actually done it. His bombsight was achieving accuracy that made existing systems look like Stone Age tools. Test bombardiers with minimal training were placing practice bombs within 75 feet of targets from 10,000 feet. 75 feet. That wasn't just better than existing bomb sites. That was a completely different category of precision. The pickle barrel claim that would later become legendary wasn't mere marketing hyperbole. Norden genuinely believed, and his test results suggested, that a properly trained bombardier using his sight could drop a bomb into a 3-foot diameter circle from 4 miles up. Whether anyone ever actually achieved that specific feat remained classified and debated, but the broader point was undeniable. Norden had transformed bombing from approximate area destruction into genuine precision targeting. The core innovation was gyroscopic stabilization, but understanding why this mattered requires understanding exactly what happens to an aircraft at 25,000 feet over enemy territory. Stand in an open field on a calm day. You're on a stable platform. North stays north. The horizon remains level. Point at a distant tree, and your finger keeps pointing at that tree unless you deliberately move it. Your reference frame is stable relative to the Earth's surface. Now stand on the deck of a ship in rough seas. North still stays north, but you're pitching forward and backward, rolling side to side. And if the ship is turning, yawing left or right, point at that same tree on the distant shore, and your finger draws wild circles in the air even though you're trying to hold it steady. Your reference frame is now unstable, moving independently of the target you're trying to track. A bomber at 25,000 feet is that ship, except the instability is worse. Much worse. Aircraft movement breaks down into 3 axes of rotation, and every single one of them destroys your bombing solution instantly. Pitch is the nose going up or down. When a bomber climbs or descends, even slightly, the bombardier's view of the ground tilts. A 3-degree pitch change, barely noticeable to the crew, translates to more than 1,000 feet of error in the bomb's impact point. Roll is the aircraft tilting left or right along its longitudinal axis. When the wings aren't level, the bombardier's view rotates around the center line. A 2-degree roll, a tiny banking motion, adds 600 feet of horizontal error. Yaw is the nose swinging. left or right, while the wings stay roughly level. This happens constantly, as pilots make minor rudder corrections to maintain heading in crosswinds. Your errors are harder to quantify because they interact with forward velocity, but they're equally destructive to bombing accuracy. In a perfectly trimmed aircraft flying through absolutely calm air with an expert pilot making no control inputs, you might have 3 or 4 seconds of relative stability. But calm air at 25,000 feet doesn't exist. Jet streams create turbulence. Temperature variations between air masses generate updrafts and downdrafts. The wake turbulence from other bombers in formation causes constant buffeting, and that's before anyone starts shooting at you. When German 88mm flak batteries opened fire, their shells detonated at preset altitudes, creating shrapnel clouds that rocked bombers like toys. Aircraft subjected to near-miss flak bursts could experience 10 or 15 degrees of teet, pitch and roll simultaneously. Pilots fought constantly to maintain straight and level flight. The aircraft never stopped moving. Here's what that movement meant for bombing calculations in the pre-Norden era. You're a bombardier in 1940, using a Sperry or Mark 15 sight, tracking a factory through your optics. You've spent 20 seconds getting everything aligned. Airspeed 180 miles per hour. Altitude 20,000 feet. You've estimated wind correction at 15 degrees left based on drift calculations. You've determined that you need to release in exactly 12 seconds when the target reaches your crosshairs. Perfect. Then, a gust of wind hits the bomber. The nose pitches up 3 degrees. Your bomb trajectory just changed by over 1,000 feet. Your bomb, which was going to hit the factory, will now land in the neighborhood a quarter-mile beyond it. But before you can recalculate, the aircraft is rolling 2 degrees right as the pilot corrects for the pitch, which adds another 600 feet of horizontal error. And you still have 11 seconds until release, during which the aircraft will move at least a dozen more times. Experienced bombardiers developed intuitive compensation methods. They'd watch the target drift in the sight and make gut-level corrections, releasing early or late based on accumulated experience. The absolute best bombardiers, men like Captain Lewis Carrington, who trained at Lowry Field in Colorado, could feel the aircraft's movement through their entire bodies and compensate subconsciously, achieving accuracy that seemed almost supernatural. But this wasn't a teachable skill. This was an art form that took years to develop, and the Army Air Forces needed to train thousands of bombardiers in months, not years. The British had already concluded the problem was unsolvable, which was why they'd abandoned daylight precision bombing in favor of nighttime area bombing. If you can't hit a specific factory, hit the entire city and accept the civilian casualties as unavoidable. American doctrine rejected that approach, partly for humanitarian reasons, but mostly for practical strategic calculation. Military planners believed that precision targeting of critical industrial nodes would cripple Germany's war machine faster and more efficiently than carpet bombing entire urban areas. But precision required solving the movement compensation problem, and only Carl Norden had solved it. Norden's breakthrough came from understanding a physical principle that had been known since the 1850s, but never properly weaponized: gyroscopic rigidity in space. Take a bicycle wheel, spin it rapidly, and try to tilt it. The wheel resists. It wants to maintain its orientation. Spin it faster, and the resistance strengthens dramatically. This isn't magic or electromagnetic force. It's conservation of angular momentum, one of the fundamental laws of physics discovered by Jean-Bernard Léon Foucault in 1852. A gyroscope is simply a wheel spinning inside a frame, but that frame is special. It's called a gimbal, and it allows the wheel to rotate freely in any direction, while the wheel itself maintains its original orientation. You can pick up a gyroscope, flip it upside down, shake it violently, spin around in circles, and that wheel inside refuses to change its orientation. It's locked onto a reference axis in space and maintains that reference regardless of what happens to the frame around it. Here's why this property is extraordinary for bombing. If you mount a gyroscope in an aircraft and spin it up before takeoff, that gyroscope locks onto Earth's gravitational vertical. The aircraft can pitch, roll, and yaw simultaneously. The gyroscope doesn't care. It maintains its original orientation relative to the ground, not relative to the aircraft. It's like having a tiny piece of stable ground floating inside your unstable bomber, an island of reference in a sea of chaos. Norden realized this solved everything, but only if implemented correctly. A single gyroscope could only maintain reference in one plane. Aircraft move in 3 dimensions simultaneously. The Mark 15 Norden Bombsight, which entered final development in 1931, used a 3-axis gyroscope system. 3 separate spinning wheels, each mounted in its own gimbal assembly, each maintaining reference for a different axis of aircraft movement. The primary gyroscope handled pitch and roll stabilization. It spun at approximately 8,000 revolutions per minute, powered by a vacuum pump that drew air through the system using the Venturi effect. This wasn't a small toy wheel. The rotor was approximately 4 inches in diameter, machined from hardened steel, precisely balanced to eliminate any wobble that would degrade performance. At 8,000 RPM, that rotor stored enormous angular momentum, creating resistance to deflection so strong it was nearly impossible to move by hand. The secondary gyroscope handled directional stability, maintaining the sight's heading reference even as the aircraft yawed during turns or in crosswinds. This gyroscope operated at slightly lower RPM, around 6,000, but with equally precise balancing requirements. The tertiary gyroscope integrated with the automatic pilot system that Norden developed for later models, allowing the bombsight to physically control the aircraft during the final bomb run. This integration, implemented in the Mark 15 Mod 4 variant deployed in 1943, represented perhaps Norden's most audacious innovation. The bombardier, not the pilot, flew the aircraft during the critical minutes before bomb release. But gyroscopic stabilization only solved half the problem. Maintaining a stable view of the ground didn't automatically calculate when to release the bombs. That required building one of the most sophisticated mechanical computers ever created in the 1930s. The complete Mark 15 bombsight weighed 50 pounds and contained over 2,000 precision parts. Many components were machined to tolerances of 1/10,000th of an inch, precision that challenged even the best machine shops in America. Each bombsight required approximately 200 hours of hand assembly and calibration. Every gear had to mesh perfectly. Every bearing had to spin without detectable friction. The optical system required alignment accurate to fractions of a degree. And all of this had to work reliably in operational conditions that would destroy most precision instruments. Temperatures ranging from -60 degrees Fahrenheit at altitude to +120 degrees on the ground, air pressure at 1/3 of sea level, constant vibration from 4 Wright-R 1,820 cyclone radial engines, each producing over 1,000 horsepower, and violent maneuvering during combat. The system started with power generation. The gyroscopes needed continuous power to maintain their 8,000 RPM operating speed. This required a dedicated vacuum pump mounted in the aircraft fuselage, driven by the electrical system. The pump pulled 7.5 cubic feet of air per minute through the gyroscope housings, spinning the rotors through aerodynamic force. Bombardiers had to activate this pump at least 15 minutes before the bomb run to allow the gyroscopes to reach full speed and stabilize. If the pump failed, or if the gyroscopes didn't reach proper RPM, the entire sight became useless. Many missions were aborted or bombed with reduced accuracy because of gyroscope power failures. Once the gyroscopes reached operating speed, they created what Norden called the stable vertical, an artificial horizon that ignored everything the aircraft was doing. The bombardier's telescope was physically mounted on a gimbal system connected to the primary gyroscope through a series of precision gears and linkages. When the aircraft pitched up 5 degrees, the gyroscope maintained its level orientation, and the mechanical linkages automatically tilted the telescope down 5 degrees relative to the aircraft structure. The result: the bombardier's view stayed locked on the same spot on the ground. When the aircraft rolled, the gyroscope compensated by counter-rotating the telescope mount. The bombardier saw a stable view as if the aircraft wasn't moving at all. This stabilization happened through what engineers would today call a mechanical feedback loop. The gyroscope detected deviation from level. That deviation rotated a gear. The gear adjusted the telescope position through a cam and follower mechanism. The telescope stayed locked on target. All of this occurred mechanically, with no electronics, no computers in the modern sense, just precisely machined metal parts transferring rotational force through the system at the speed of physics. But stabilization was only the first function. The sight also had to calculate the correct release point, and this is where Norden's mechanical genius truly manifested. The bombardier input airspeed using a dial on the left side of the sight, reading the value from the aircraft's pitot-static instruments. He input altitude using another dial. But here's where the Norden became genuinely intelligent. It measured actual ground speed automatically by tracking how fast landmarks moved past the crosshairs during the approach. This automatic ground speed calculation was essentially mechanical calculus. A disk and drum computer inside the sight continuously compared the rate at which the bombardier had to adjust the telescope to keep the crosshairs on target against the input airspeed and altitude. The difference between indicated airspeed and actual ground tracking rate revealed wind velocity and direction with far greater accuracy than any manual estimation method. This mechanical computer used differential gears, cams, and circular slide rules machined into bronze discs. As the bombardier tracked the target during the 30-second approach, these components rotated against each other, physically solving the ballistic equations. The computer calculated trail, how far forward the bomb would travel during its fall. It calculated drift, how far wind would push the bomb sideways. It calculated range, the actual ground distance to target, after accounting for altitude and approach angle. All these calculations fed into Norden's synchronous bombing method. The bombardier kept the crosshairs on target, while the sight's computer continuously recalculated the perfect release point. Not when the target appeared at a certain position in the sight, but when the aircraft reached the exact 3-dimensional coordinates in space, where releasing the bomb would result in a hit. When that point arrived, an electrical circuit completed. The bombardier pressed the release trigger, and the bombs dropped. The beauty of the system was its automation. The gyroscopes compensated for movement. The mechanical computer solved the mathematics. The bombardier simply had to keep the crosshairs steady and trust the machine. In theory, a moderately trained bombardier using a Norden sight should achieve accuracy comparable to an expert using any other bomb sight. In theory, human skill became less critical than machine precision. Testing began in earnest in 1933 at the Naval Proving Ground near Dahlgren, Virginia. Norden himself supervised the trials, flying in observation aircraft while Navy bombardiers dropped practice bombs on target rafts floating in the Potomac River. The early results were classified at the highest levels, but internal Navy documents declassified decades later reveal something remarkable. Bombardiers with minimal training, men who'd never dropped a live bomb before, were consistently placing practice ordnance within 75 feet of target rafts from 10,000 feet altitude. 75 feet. The best bombardiers in the world, using any other sight, couldn't match that accuracy with years of experience. The Army Air Corps immediately ordered their first production batch in 1933, but imposed security measures that seemed paranoid even by military standards. Each sight received a unique serial number tracked through a dedicated logbook. Each sight required 2 armed guards whenever it moved from storage to aircraft. Bombardiers swore a formal oath, separate from their general security clearance, specifically about the Norden sight. The oath promised never to discuss the site's mechanisms or capabilities with anyone lacking proper authorization. Violating that oath was designated treason, punishable by up to 20 years in federal prison and a $20,000 fine. When bombardiers trained at facilities like Lowry Field in Colorado, Midland Army Airfield in Texas, or Victorville in California, the Norden sights were stored in dedicated vaults with combination locks. Only 3 people on each base knew the combinations. Before each training flight, armed guards removed the sight from the vault, escorted it to the aircraft, watched the bombardier install it in the nose section, and remained with the aircraft until the flight ended and the sight returned to the vault. If an aircraft carrying a Norden sight experienced mechanical problems away from base, armed guards were dispatched immediately to secure the device, sometimes before anyone bothered to check if the crew was injured. This wasn't security theatre. The Norden sight represented nearly 15 years of engineering development and somewhere between $1.5 and $2 billion in total program costs calculated in 1940s dollars, equivalent to roughly $30 billion today. Each individual bomb sight cost approximately $8,000 to manufacture. For comparison, a complete B-17 bomber cost around $238,000, including 4 engines, defensive armament, and accommodations for a 10-man crew. The Norden sight was 50 pounds of gears and gyroscopes that cost $8,000. By 1940, Norden's Brooklyn facility was producing about 50 sights per month. That number climbed to 200 per month by 1942 and eventually exceeded 600 per month by 1944. Total wartime production reached approximately 50,000 units. Each required individual hand-fitting and calibration. This wasn't mass production in Ford's assembly line sense. It was precision instrument manufacturing scaled up to wartime demand through parallel production lines. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The security extended to combat operations. Before every mission over Europe, bombardiers signed out their assigned Norden sight from the base armourer, signed it back in after landing. If a bomber was shot down over enemy territory, the bombardier was explicitly instructed to destroy the sight before bailing out or crash landing. Special thermite charges were installed for this purpose, chemical incendiary devices that burned at over 3,000 degrees Fahrenheit, hot enough to melt the bronze gears and aluminum housings into unrecognizable slag. Several bombardiers died trying to destroy their sights rather than abandon them to German capture. Second Lieutenant Robert Fay-Moyer remained at his bomb site despite severe injuries during a mission over Merseburg in November 1944, successfully destroying the device with thermite before the aircraft crash-landed. He died of his wounds but received the Medal of Honor posthumously, partly for his determination to protect the Norden. The Germans knew about the Norden through intelligence reports and desperately wanted one for reverse engineering. Their own Luftwaffe 7 bomb sight, while adequate for level bombing, lacked the Norden's gyroscopic stabilization and automatic trajectory calculation. Several Luftwaffe units were specifically tasked with attempting to capture intact B-17 seconds or at least retrieve Norden sites from crash sites before Allied recovery teams arrived. They succeeded exactly once. In March 1943, a B-17 from the 306th Bomb Group made an emergency landing near Brest, France, with minimal damage. German troops secured the aircraft before the crew could properly destroy the equipment. The Norden site was recovered intact and transported to the Luftwaffe testing facility at Rechlin. German engineers spent 3 months examining it, creating detailed technical drawings and attempting to reverse engineer its mechanisms. Their final report, captured after the war and declassified in 1973, makes fascinating reading. The German analysts concluded that while they understood the basic principles, duplicating the Norden was impossible with Germany's available manufacturing capabilities. The precision machining required exceeded what German industry could produce at scale. The gyroscope bearings alone demanded tolerances Germany couldn't reliably achieve. More significantly, the report concluded that even if Germany could manufacture copies, training bombardiers to use the complex device effectively would take at least 2 years per bombardier, time the Luftwaffe absolutely didn't have. The Norden wasn't just technologically superior. It was so complex that capturing one provided no practical advantage. Carl Norden himself became a ghost during the war years. He refused all interview requests, avoided any publicity, and continued refining the site based on combat feedback reports from Europe and the Pacific. The man who'd promised pickle barrel accuracy had delivered something close enough to it that strategic bombing doctrine became viable. Now the question was whether it would actually work when conditions were far from ideal, when enemy fighters were attacking and flak was exploding and men were dying. The answer came on August 17, 1942, when 12 B-17 bombers from the 97th Bombardment Group attacked the Rouen-Sotteville railway marshalling yards in occupied France. Each bomber carried a Norden sight. Each bombardier had trained for months on the device. The mission briefing promised surgical precision. Hit the rail yards. Avoid the civilian housing 400 yards away. Prove that American daylight precision bombing could work. The after-action reports tell a more nuanced story than the public relations releases suggested. Of the 36,000 pounds of bombs dropped that day, approximately 50% landed within 1,000 feet of the aiming point. 50% within 1,000 feet. That's not pickle barrels. That's not even individual buildings. That's a quarter-mile circle. But context matters. This was under nearly ideal conditions. Light flak, no fighter opposition, clear weather, minimal combat stress. As the war progressed and missions pushed deeper into Germany against heavier defences, reality diverged from testing range results. The 8th Air Force maintained meticulous bombing accuracy records throughout the war, classified until decades after VE Day. By 1943, they were flying hundreds of sorties monthly against German industrial targets, and the statistics were humbling. Under actual combat conditions, with enemy fighters, heavy flak, and battle-hardened crews, average accuracy was approximately 300 to 400 feet circular error probable, meaning half of all bombs landed within 300 to 400 feet of the bombardier's aim point. That's still revolutionary compared to 1940 standards, when 400 feet was considered excellent accuracy. But it's nowhere near the 75-foot accuracy achieved during peacetime testing at Dahlgren. Several factors explain the degradation, and understanding them reveals the gulf between theory and reality in strategic bombing. First was flak. German anti-aircraft batteries evolved throughout the war into sophisticated defensive networks. By 1943, major industrial targets were defended by dozens or even hundreds of 88mm guns coordinated through central fire control. These weapons fired proximity-fused shells that detonated near bombers automatically, creating shrapnel clouds that ripped through aluminum skin and hydraulic lines. When jagged steel is punching through your aircraft at 25,000 feet, killing the navigator beside you, filling the fuselage with smoke and the smell of burning metal, maintaining concentration on the Norden sight's crosshairs becomes extraordinarily difficult. Bombardiers reported that during heavy flak, their hands shook so badly they couldn't keep the sight steady. The Norden's gyroscopes compensated for aircraft movement, but they couldn't compensate for human terror. Fighter attacks created worse problems. When Messerschmitt Bf-109s or Focke-Wulf T-190 fighters came screaming through the formation at 400 miles per hour, firing 20mm cannons that could saw a bomber in half, aircraft had to take evasive action immediately. Violent maneuvering, hard banking, diving, climbing, all movements that overwhelmed even the Norden's sophisticated stabilization systems. Many bombardiers during fighter attacks simply salvoed their entire bomb load and focused on survival rather than accuracy. Mission reports contain dozens of entries like "Bombardier released early due to fighter pressure" or "Formation scattered, bombing results unknown." The Norden couldn't help if the bombardier wasn't looking through it. Weather was the silent destroyer of precision. The testing at Dahlgren occurred in clear visibility. Over Germany, cloud cover frequently obscured targets completely. Even with the Norden sight, you cannot hit what you cannot see. By 1944, the 8th Air Force increasingly used radar-assisted bombing techniques like H-2X for missions with poor visibility, essentially abandoning the Norden and dropping bombs based on radar images of cities and terrain features. Accuracy with radar bombing plummeted to over 1,000 feet, circular error, sometimes much worse. The Pacific Theater presented different challenges. Against Japanese shipping and island installations, the Norden worked somewhat better because ships and concrete bunkers were easier to identify and track than camouflaged German factories nestled in urban areas. The 5th Air Force, operating B-17 seconds and later B-29 superfortresses in the Pacific, reported moderately better accuracy, averaging 250 to 300 feet against major targets. The mission against the Mitsubishi aircraft plant in Nagoya on December 13, 1944 achieved 28% of bombs within 500 feet of the aiming point, considered excellent under combat conditions. But even that success highlights the gap between promise and reality. 28% within 500 feet meant 72% of bombs missed by more than 500 feet, nearly 2 football fields. The Norden had made bombing dramatically more accurate than 1940 standards. But it hadn't delivered miracles. Strategic bombing remained as much art as science, dependent on courage and persistence as much as technology. Yet dismissing the Norden as overhyped or a failure fundamentally misses what it accomplished. Before Norden, bombardiers aimed through crude optical sights and guessed. After Norden, they used gyroscopically stabilized instruments that automatically computed ballistic trajectories. The technology didn't deliver perfection, but it elevated bombing accuracy from medieval guesswork into Taimanasci, engineering science. More importantly, the principles Norden pioneered became the foundation of every precision guidance system developed afterward. The direct lineage runs through Air Force research programs in the 1950s, when engineers working on early cruise missiles faced the same fundamental problem Norden had confronted. How do you guide a weapon to a target when the weapon itself is moving through three-dimensional space? The answer was inertial navigation systems, direct descendants of Norden's gyroscope assemblies. The MGM-13 Mace cruise missile, deployed in 1959, used 3 gyroscopes to maintain spatial reference exactly as the Norden sight had, except now the gyroscopes were controlling flight surfaces rather than bombsight optics. By the 1960s, gyroscopic inertial navigation systems were standard equipment on strategic bombers, ballistic missiles, and even commercial aircraft. The Boeing 747, first flown in 1969, used triple redundant inertial navigation units to cross oceans without ground-based navigation aids. Each unit contained 3 gyroscopes, maintaining reference on 3 axes: pitch, roll, and yaw. The basic architecture was Carl Norden's 3-axis stabilization system, miniaturized and enhanced with electronics instead of mechanical computers. Modern weapons have evolved beyond mechanical gyroscopes into ring laser gyroscopes and fiber optic gyroscopes, but the underlying principle remains identical. The AGM-86 cruise missile, deployed in the 1980s and still in service today, uses inertial navigation to fly hundreds of miles to targets with accuracy measured in feet, not miles. The Tomahawk cruise missile combines inertial navigation with GPS and terrain-matching radar. But when GPS is jammed or unavailable, it falls back on pure inertial guidance, trusting gyroscopes to maintain spatial reference exactly as Norden's bombardiers did over Europe. Drone technology represents perhaps the purest expression of Norden's vision. The MQ-9 Reaper and other unmanned combat aircraft use inertial measurement units containing accelerometers and gyroscopes that provide continuous data about the aircraft's orientation and movement. This data feeds into flight computers that stabilize the aircraft and calculate weapon trajectories automatically. The human operator designates the target. The machine handles everything else. That was precisely what Norden tried to achieve, removing human error from the bombing equation by letting stabilized instruments handle the calculations, while the operator simply maintained target tracking. Even smartphones contain Norden's legacy. The gyroscope chip in a modern phone, measuring just a few millimeters across, detects rotational movement using vibrating silicon structures instead of spinning wheels. But it performs the same essential function Norden's 4-inch steel rotor performed in 1940, maintaining a reference frame for calculating position and orientation in 3-dimensional space. Carl Norden never got his literal pickle barrel, but he achieved something more significant. He proved that gyroscopic stabilization could solve previously unsolvable problems in guidance and navigation. Every precision weapon, every autopilot system, every inertial navigation unit used today traces its conceptual lineage back to a Swiss-born engineer who spent 15 years obsessing over spinning wheels and gimbal frames in a Brooklyn workshop. The morning after the Ham raid, Oberst Friedrich Weber filed his report to Berlin with a single devastating conclusion. The Americans have solved the bombing problem. Our industrial infrastructure is now vulnerable in daylight. German intelligence services intensified their efforts to understand the Norden, but the technology gap proved insurmountable. By late 1943, Albert Speer's armaments ministry was relocating critical production facilities underground, not because American bombs were particularly powerful, but because they were hitting exactly what they aimed at with terrifying consistency. The final statistics tell the story. Between August 1942 and May 1945, American heavy bombers conducted over 600 major strategic bombing operations against German industry. 83% achieved their primary objective, stopping production at the targeted facility for at least 30 days, or reducing output by 50% for 90 days or more. That 83% success rate came at brutal cost. 26,000 8th Air Force airmen killed in action, another 28,000 wounded, 18,000 captured. More than half of all combat aircrew became casualties. But those casualties accomplished what they were intended to accomplish. Germany's industrial capacity collapsed systematically, not from random destruction, but from precision, targeting of irreplaceable components in an integrated manufacturing system. The Norden Bombsight didn't win World War II by itself. No single weapon ever does. But it transformed strategic bombing from theoretical doctrine into practical reality, from approximate area destruction into genuine precision warfare. And every guided weapon that followed, from Vietnam-era smart bombs to modern cruise missiles, carries Norden's engineering DNA in its guidance systems. Carl Norden died in 1965, largely forgotten by the public. His obituary in the New York Times ran 4 paragraphs. But his legacy flies in every aircraft, guides every missile, and stabilizes every smartphone. The pickle barrel became the precision-guided munition. The dream became reality. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.